Hello, everyone, and thank you for joining us today for this webinar with Task Force and Roden Schwartz from the Test Essentials series, Vector Network Analyzer Basics. Before we get started, I just want to go over a few housekeeping items. This webinar is going to be recorded, and everyone who signed up will receive the recording in an email afterwards. You're free and encouraged to share this email with anyone that you think might be interested in the presentation. And you'll also have the ability to go in and rewatch the webinar at any time at your own pace. We'll go through the presentation and then we'll have some time at the end for any questions. If you think of a question during the presentation, please just put it in the Q&A box. It should be on your right-hand side of your screen, and then we'll get to your question at the end of the presentation. Or if you'd rather unmute yourself and speak at the end of the presentation, you can just raise your hand and we'll call on you to ask your question. Today's presenter is Greg Bonagide. He is a senior applications engineer from Roden Schwartz, specializing in spectrum analyzer and vector network analyzer technology. He's worked in the RF and microwave field since 1982 in design, systems engineering, and test and measurement roles. Without further ado, let's get started.
In this Test Essentials webinar, we'll begin by looking at a few applications typically associated with a vector network analyzer. Next, we'll answer the question, how does it work, by examining the unique architectural features of a VNA, and then examine some common measurements performed by a VNA. There are a number of VNA models available on the market today, so it's worth taking a moment to examine the similarities and differences. Fortunately, every VNA has a common set of controls necessary for setting up a measurement, so we'll discuss these and then present key terms that are frequently associated with VNA measurements. We'll then examine the VNA test setup, highlighting the various components needed for calibration and measurement. Then we'll walk through the steps required to prepare a VNA for measurement, using a DUT's listed requirements as a starting point. Finally, we'll discuss VNA accessories needed to meet common test requirements, as well as options required for unconventional VNA applications. Let's get started. We'll start our presentation with a bold statement. The VNA is the most versatile and accurate instrument for measuring RF components. It is versatile because it makes all its measurements using the most fundamental type of radio frequency signal, a continuous wave. Continuous waves have constant amplitude and frequency. With a continuous wave signal, the phase is determined by the relative placement of the generator and receiver, as well as by electrical influences of the device under test. The VNA is accurate because it uses system error correction to greatly reduce the influence of unwanted losses and reflections. So the VNA's major task involves generating a continuous wave signal and measuring its amplitude and phase at different points. Most often, these measurement points coincide with the ports of the device under test. But wait, there's more. The VNA can repeat these measurements over hundreds or thousands of frequency points for a wide variety of active or passive devices. Primary measurements include RF energy transmitted through a device and RF energy reflected from the ports of a device. These types of measurements are useful for impedance matching, loss measurements, which are particularly important for passive devices like transmission lines and microwave filters, gain measurements, which are important for active devices like amplifiers, and measurements of electrical delay or phase, which are very important for phased array antennas. Typical VNA applications cover all design stages, from research and development to device characterization to high-volume manufacturing test. Some common passive devices include antennas, filters, power combiners, signal splitters, interconnect backplanes, coaxial cables, connectors and adapters, and mixers. Common active devices include amplifiers, both low-noise amplifiers and power amplifiers, as well as active planar antenna arrays, front-end modules, up-down converters, as well as higher-level RF subassemblies. A VNA consists of 1, 2, 4, or more RF ports. Each one of these ports contains a reflectometer, which in modern VNAs contains two receivers, one for sampling the incident wave called the reference receiver, and one for sampling the reflected wave, called the measurement receiver. This naturally requires a wave-separating device for sampling the incident and reflected waves. Two common devices are the VSWR bridge and the RF or microwave directional coupler. Bridges are better suited for lower frequency applications, up to a few gigahertz, whereas directional couplers provide excellent broadband performance extending from 1 GHz to 67 GHz or higher. All VNAs also require at least one RF generator or source. This generator produces a continuous wave signal at each measurement frequency. A switch or other device is used to apply the generator's output to each VNA port, one at a time. Besides these functional blocks, auxiliary components may be required for particular applications. These may include receiver as well as generator attenuators or pulse generators and modulators. How does this architecture change if you increase the port count? Basically, you need to add a new reflectometer for each additional port. Here, we show a block diagram of a 4-port device, which has 4 reflectometers. Generally, a multi-port instrument requires only a single generator for S-parameter measurements. However, extra generators are sometimes needed for advanced applications, like measuring two-tone transmitter intermodulation distortion, or providing local oscillator signals for frequency-converting devices. What makes a VNA's architecture so special? To understand this, we must examine individual components that make up a VNA and see how they are integrated together. For example, the VNA's reference and measurement receivers must be very linear so they can deliver accurate power ratios over wide signal levels. This is a necessary prerequisite for accurate S-parameter amplitude measurements in dB. Phase measurements, on the other hand, require coherent clocking of all receiver local oscillators. This means careful attention must be paid to the design of the LO distribution network and the placement of the receivers within the VNA so that coherence is maintained over temperature and time. The VNA receivers and generators are also tightly synchronized to ensure proper frequency settling and the fastest possible measurement speeds. Besides these internal architectural considerations, a VNA test system also generally consists of external components like test fixtures and other circuitry that can impact the electrical characteristics of the device to be tested. The VNA has no way of anticipating what is connected to its test ports, so it relies on system error correction to remove these effects. Typically, VNA calibration involves connecting test standards representing a short circuit, an open circuit, and a 50 ohm load or match to each test cable as prompted by the calibration routine, and then inserting a through standard to the end of the 2 test cables. Today, this process can be simplified through the use of an automatic calibration unit, also known as eCal, which contains these test standards and automatically switches between them, greatly speeding up the calibration process and reducing the chance of operator error by connecting the wrong standard during any step of this process. In this first measurement example, the frequency response of a small 7-element Yagi antenna is measured. The setup is simple. The antenna is simply connected to port 1 of a calibrated VNA, and the antenna under test is positioned in an area free of reflections or else placed in an RF test chamber. In this example, the manufacturer specifies an operating frequency range of 1850 to 1990 MHz. When measured, the VNA markers show that the return loss is better than 15 dB in this frequency range. But the return loss is purely a magnitude measurement. Sometimes phase information is desired as well. A good example is the Smith chart, which shows both amplitude and phase of reflections. A VNA allows you to electrically move the measurement plane to the antenna-driven element, which changes the resulting impedance. Here we use the offset embed function to accomplish this, and you can see how it impacts the impedance at the markers. To measure a small amplifier, the VNA may be set up as shown here. Typically, amplifier measurements require a S-parameter calibration and a power calibration with a power meter. Besides setting up a simple frequency sweep, a power sweep may be used to show an amplifier's gain compression characteristics. Here, the input power is swept from -30 to +5 dBm, and the small signal gain is seen to compress by 1 dB at an input level of 0.35 dBm. This is called the input 1 dB compression point. The VNA also displays the output 1 dB compression point of 20.5 dBm, which is simply the input compression point plus the measured compressed gain value. For this and other amplifier applications, it is wise to check for VNA receiver compression. Higher-end VNAs have mechanical attenuators built in that make this easy. Here, we increase the measurement receiver attenuation in 5 dB steps until the measured 1 dB compression point remains steady. It's also a good idea to ALC or automatic level control, especially if the application calls for high power accuracy or if the amplitude is very sensitive to drive level. Sometimes the harmonics produced by an amplifier are of interest. Here we are measuring harmonics in two ways. In the upper right-hand diagram, we are performing a frequency sweep at a fixed power level, showing how the fundamental green trace, second harmonic blue trace, and third harmonic orange trace vary with frequency. Consider that while we're sweeping the generator from 10 MHz to 5 GHz, the receiver we're using to measure the third harmonic must sweep from 30 MHz to 15 GHz, so a power calibration over this entire frequency range is required. In the lower left-hand diagram, we are performing a power sweep from -30 dBm to 5 dBm at a fixed frequency of 1 GHz. Here, the green trace represents the input power, the blue trace shows the fundamental output power, the orange trace shows the second harmonic, and the red trace shows the third harmonic power. There are a wide range of VNA models available on the market today. Fortunately, they may be differentiated by only a few important characteristics. The first important characteristic is operating frequency range. Here, lower-cost models are typically limited to operation below 1 GHz, whereas higher performance models may sweep across microwave and even millimeter wave frequencies. Second, VNAs are classified by their number of ports. While some single-port VNAs exist, the vast majority of VNAs have 2 ports. With the advent of balanced circuitry and transmission lines, VNAs with 4 or more ports have become more common. Another advantage of some multi-port VNAs, like the Rohde and Schwarz ZNBT, is that they can be configured to operate in parallel mode so that the DUT test throughput can be increased for high-volume RF test applications. Another interesting application is testing of complex devices like front-end modules, which have multiple RF inputs and outputs. The final VNA classification is whether the instrument has a built-in user interface or not. Often, faceless instruments rely on the processing power of an external PC and are generally mouse-driven. Instruments with built-in screens and buttons are completely self-contained and often easier to operate on a bench. What are the key controls needed to set up and operate a VNA? An operator will usually set the stimulus type and range first. The default stimulus type is a frequency sweep, where the user establishes the start and stop frequencies or the center frequency and span. Another important stimulus type is the power sweep, which we've already seen used in amplifier measurements. For a power sweep, the user sets the starting and ending power values and also the fixed frequency at which the power sweep is to be executed. Conversely, for a frequency sweep, the fixed power level must be specified. Another important control is the number of measurement points. Since S parameters must be calculated for each measurement point, increasing this number will slow down the sweep. The receiver IF bandwidth setting impacts both the noise floor and the sweep speed. A smaller IF bandwidth reduces the noise floor and improves the instrument's dynamic range, but at the cost of a slower sweep speed. Conversely, wider IF bandwidths reduce the sweep time considerably, but at the penalty of a higher noise floor and reduced dynamic range. The final important VNA control is the calibration or system error correction method. As noted earlier, calibration is essential for removing unwanted attenuation and reflections that would otherwise degrade measurement accuracy. The most widely used and popular calibration method of the last 40 years is the TOSM, or Through Open Short Match method, also known as SOLT for Short, Open, Load, and Through. Another method gaining in popularity is the UOSM method, which is operationally very similar to the TOSM method, except that an unknown reciprocal through device may be substituted for the previously characterized through cal standard. When shopping for a VNA, here are key terms to consider for evaluating different performance metrics against your application's requirements. Frequency range. Will you need to make only in-band measurements, or are out-of-band measurements required as well? Examples of the latter might be harmonic measurements for amplifiers or the stop-band performance of a bandpass filter. Dynamic range. This is a measure of the difference between the maximum power and noise floor of an instrument. Again, consider this in light of your application. If you need a wide dynamic range for a production application, you may have to sacrifice noise floor by using a wider IF bandwidth to maintain an acceptable sweep time. This might require a higher performance instrument to meet these conflicting needs. Measurement speed is intrinsically linked to your dynamic range requirements. Banner specs for sweep speed are often provided for wide IF filter settings. Also, check the fine print. Are the sweep times mentioned in the specifications based on a 1-port or 2-port calibration? Make sure you consider the values that coincide with the needs of your application. Trace noise. How much jitter is there on a trace? Less jitter is better, but often the effects of thermal noise associated with limited dynamic range will greatly outweigh the tiny values of trace noise specified on a datasheet. Measurement stability. How much measurement drift is observed over time and changes in temperature? Will you be operating the instrument in a climate-controlled environment? The sensitivity of the VNA to temperature changes, combined with performance demands of your application, may drive how often you'll need to perform calibration, hourly, daily, or weekly. Keep in mind that measurement stability is also a function of all the components in your setup, especially cables. Inexpensive or old, worn test cables can have a huge impact on measurement stability and repeatability. System error correction. Which type is best suited to your application? Does the VNA you are considering support this correction method? While most VNAs provide the TOSM method as standard, some may not support the TRL or TNA methods, which can be vital for de-embedding test fixtures from DUT measurements. What equipment is generally required for a VNA setup? The first is obviously the VNA itself, with performance suitable for the application at hand. Next, you'll need phase-stable test cables appropriate for the demands of the application. Torque wrenches must be used to ensure repeatable RF performance. These are required where the test cables connect to the VNA and also where they connect to the device under test. A cal kit is required for calibration or system error correction. Both manual cal kits and auto cals are available today. Finally, power sensors are required for applications where accurate absolute power measurements are necessary, such as with amplifier measurements. The VNA measurement process begins with setting the appropriate values of the key controls to configure the necessary measurements for the DUT. We mentioned in an earlier slide that this involves setting the stimulus type and range, power levels, number of measurement points, and IF bandwidth. Next comes calibration, which compensates for unwanted reflections and attenuation due to cables and test fixtures, and, if a power sensor is used, transfers absolute power measurement accuracy from the sensor to the VNA receivers. After completing calibration, the DUT is inspected to ensure proper DC biasing and connections. It is then connected to the VNA and measurements are made. Any required tuning, such as aligning RF filters, can be performed. Finally, trace data may be exported for archiving, for reports, or to be used in RF simulation programs. Next, we'll demonstrate this measurement process for a low-pass filter. Okay, so the first thing we're going to do is start from a preset, and now we're going to set our start frequency to 2 megahertz, and we're going to change our frequency step size to 2 megahertz. That'll give us 3,000 points. Now we're going to do a calibration with an AutoCal unit. And I'm just going to start the calibration sweep. Doing the open short match at each port, and then we'll do a through and we'll be done. Okay, we're done, so I'm going to apply the cal, and I want to save it into our cal manager. So I'm going to add it and change the name of it to something more memorable. So I'm going to call it the 2-port UOSM cal. And now we're done here. Next thing to do, I want to remove the AutoCal unit, and I'm going to attach my DUT, which is a low-pass filter with a cutoff frequency of about 1.8 gigahertz. So I want to recall a setup I previously did for this configuration. And initially it doesn't have any calibration assigned to it, so I'm going to apply the cal that I just performed to this setup. And you can see here now I've got a marker. You can see a very nice low-pass filter response. And I can move that marker around here in the stop band a little bit to see its response. But if I couple the markers together, all the markers move simultaneously. Here I've introduced a new kind of plot called a polar plot in the lower right-hand diagram area. And this is interesting because it shows amplitude and phase of the transmission characteristic simultaneously. And you can see as I move the markers around, particularly between 1.5 and 1.7 gigahertz, we see that the phase actually changes about 45 degrees. And now I'm turning off the cal, and you can see the difference. It hardly impacts the transmission characteristic at all, as seen in the top diagram, but you can see it has quite an impact on phase. So if you're just trying to do a quick go, no-go check of the filter, you might want to just use the built-in factory calibration. But if you're interested in phase response, you really need a complete 2-port cal. We've already mentioned several important accessories like phase-stable test cables, calibration kits, and power sensors. But there are a number of other measurement options that may be required for your unique application. For example, if you're measuring a frequency converting device like a mixer or down converter, or want to make harmonic measurements on an amplifier, the ZNB K4 frequency conversion option allows you to separate the generator from the receiver frequency. This capability is not required for conventional S parameters, which by definition are measured using the same generator and receiver frequency. Other active devices may require bias tees to supply DC voltage via the input or output RF test cables. More complicated test devices, like front-end modules, might benefit from a MIPI control interface, whereby the VNA itself sends commands to place the device into particular operating modes, speeding up testing. For amplifier tests, I mentioned the importance of receiver attenuators to prevent the VNA receivers from being overloaded by high input levels. For some extremely high-gain devices, additional source attenuation may be required to provide very low input power levels to the DUT. In this webinar, we learned that VNAs are extremely versatile measurement instruments that can provide outstanding measurements on RF and microwave components and have become indispensable tools for most every RF lab bench. VNAs are commonly used for active and passive device testing in every application phase, from early development through high-volume test. The VNA has a fairly simple block diagram consisting of one reflectometer for each port. The reflectometer contains receivers for measuring the reference RF wave and the reflected RF wave, which are separated using a directional device like a VSWR bridge or directional coupler. One or more RF generators rounds out the VNA block diagram. Calibration, also known as system error correction, is very important for removing unwanted losses and reflections from the overall test setup. The minimal VNA setup also requires, at the very least, good phase-stable cables and a cal kit to ensure accurate results. This concludes the Test Essentials webinar on VNA Basics. Thanks for watching.
Okay, we're going to open up the floor to any questions. We have both Greg Bonagide and Greg McCassell with us. So if you want to type your question into the chat, or you can simply just raise your hand and we can call on you to speak. I had a question during the presentation regarding the presentation slides, just asking if we would be able to share those with you guys. So when we share the recording of the presentation, we'll also include the slides as well. I see in the chat somebody Chris is asking if we see their question. I don't see a question. Greg, do you see it on your screen?
So I don't see any actual questions here.
Oh, I see one now from Victor K in the Q&A box. He's asking, does the VNA have other capabilities of measuring phase besides the polar graph?
Yes, for phase, you can measure it like those amplitude traces where you had amplitude versus the frequency. You can do phase versus frequency that way as well. Or of course, there's also the conventional Smith chart that's available.
I see another one here from Steph Tofolini. Pardon me if I pronounce that incorrectly. They're just asking, how difficult is it to obtain replacement parts for the analyzer? They've had a fuse for a much older one go bad, and it was a challenge to replace it.
Generally, let's say if you have a device that or an instrument that goes obsolete, we maintain the ability to repair those for, I think, at least 7 or 10 years. And beyond that, we'd use best effort for getting the replacement parts. Usually what happens are as components themselves become obsolete, it gets tougher. But generally we get notified about upcoming component obsolescence, and we'll often put in like a last buy to secure a number of those components so that they're on hand and the VNAs remain serviceable for quite some time.
Great, thanks, Greg. I've got two more questions here from Carson E, asking if you could speak to some of the applications for VNAs in power electronic design.
Yes, in power electronics, usually lower frequencies are very important. We have a couple app notes that are available on our website that address different power electronic challenges, particularly with the boards. Certainly the inherent inductance and capacitance between traces on boards become very important. And we've got a couple app notes that address that. I think they do a really good job getting into the details there. That's beyond the scope of our discussion here today, but I certainly invite you to go to our website, put in some of those keywords, and see what comes up.
Maybe Greg, if you would be able to share with me some of the links to the app notes, I could pass them on.
Absolutely, yes.
Okay, thank you. We have another question here from Edward Lai. Can VNAs be used to characterize the resonance frequencies of a quartz crystal in microbalance applications?
They can, depending on the setup. Of course, once you're starting to talk quartz crystals, you're usually talking a very high impedance. So, depending on the test fixture, if you have some way of coupling in and out of that so that you can see that high impedance and the high Q associated with that crystal without um, loading it way down, that's going to be an important part of it. But yeah, certainly a VNA can be used for that. And we do have an option, I think even starting in the mid range, where we can uh, get frequency points down in subhertz steps. So if you do have a very narrow resonance, you can very accurately characterize it from a frequency and amplitude perspective.
Okay, great. We have another question here from Abdur Rashid. Is there any possibility that a spectrum analyzer can be converted to a VNA? And what extra equipment would be needed to do that, if possible?
Yeah, good question. Uh, we've actually, well, the industry has had that kind of basic analog capability for many years uh, with a tracking generator. Generally, that gets either built into a spectrum analyzer or there's an external control line between the spectrum analyzer and the signal generator so that the spectrum analyzer and signal generator are synchronized and can do frequency sweeps. And you can see what's happening to the amplitude level versus frequency when you're measuring a device. And you can do either uh, insertion loss measurements that way, or even reflection measurements, VSWR measurements. The unfortunate thing, though, is that you do not get any phase information from that technique. But for a lot of cases, just having amplitude is sufficient. Um, but ultimately, when you want to see both amplitude and phase, you really need the VNA. The VNA is the only thing that has those coherent receivers that are comparing the incident signal from a signal generator to the reflected signal that is required for the phase information.
Okay, thanks, Greg. Another question here. If I have my VNA calibrated every year, why would I also want to have a calibration kit to make measurements?
Okay, good question. And that's a common bit of misunderstanding, I guess. We bat around that term calibration for the daily calibrations, which are really system error correction. Um, so yes, you send back the instrument once a year to get calibrated to make sure that all the hardware in the industry or in the instrument is still performing according to its specifications. But then when you get it back and in normal daily operation, you need to perform a system error correction that we also banter around as just being calibration. And the reason you need a system error correction is because the instrument itself is fine and is well characterized up to the ports of the instrument. But the VNA doesn't know what's attached to those ports. Do you have a 3-foot cable, a 3-inch cable? Do you have other like test fixtures and things like that in line? Because any and all of those components are going to affect the amplitude and phase that are right at the measurement plane, the plane at which you want to insert your device and test it. So that's why we need these daily calibrations just to remove these unwanted reflections and remove the extra attenuation that is caused by intervening cables and things. And in a perfect world, you would only have to do that once for your setup. Get the instrument, pull it out of its cardboard box or whatever, set it up, do the calibration once, and you're done. But unfortunately, in uh, in the real world, you have temperature fluctuations. Cables aren't perfect. As you bend even phase stable cables, the phase is going to change. The response of those cables are also going to change over time with wear and tear, just attaching and detaching connections to different devices under test. You may encounter situations where, for whatever reason, those connectors either get dirty or the pins get bent or something like that. And that's going to change the RF performance, particularly at higher frequencies. So because of all these reasons, and primarily kind of on a day-to-day basis, the two things that really impact the performance of the analyzer is the temperature of the environment and how much flexing of the cables are going on. If you have a very well-controlled temperature environment and you have cables that are kind of formed into the position that they need to be, where you just insert the device under test and take it out with very little movement of the cables, or maybe you have a test fixture where the device is a chip or something that just gets placed down on some pads and then eventually removed and other devices are put into place. In those sorts of situations, you can probably go a week or longer depending on the nature of the test, whether it's just high production pass-fail kind of testing, or of course with component characterization. Sometimes you have to be more careful and you can't tolerate even a tenth of a dB shift from day to day. So in something like a characterization environment, you probably want to do daily system error corrections. But something like a high volume environment, again, you don't really have any cable movement and the temperature is controlled. You can probably go a week between the system error corrections.
Got another one here. When measurements on filters, how do you know that you have enough trace points?
Well, for that situation, I guess you're probably talking about, well, it can be in different parts of the measurement of the filter. Certainly over the pass band, you want enough points if it's a bandpass filter. But you're probably speaking more to the issue of in that transition band. So a lot of times you need to make sure that your filter response is down 30 or 60 dB up to a certain frequency. Probably the best way to address that is to initially load it up with a lot of points, throw out a number like 10,000 points or something like that, or frequency spacings that are very narrow. And again, that's all going to depend on what frequency range we're talking about, megahertz or gigahertz. But anyway, as a general approach, load it up with a lot of points so that you get very detailed information about the shape of the curve. And then from there, then I would even just save that trace to memory. That's an easy thing to accomplish with certainly with our VNAs. And then just back down the number of points or spread out the amount of the frequency span between points, same difference, down to the point where you start losing that resolution that you need to be able to evaluate whether you can see everything you need to on that filter or not. The other thing we have is a segmented sweep approach. So maybe you don't need a whole lot of points in the pass band or in the far out stop band, and you're only interested in that transition region. If you set up a segmented sweep, you can break down the response of the filter into those different regions, pick the number of points you want in that region, as well as the power level and the bandwidth that you want to use for evaluating it, and pick a different set of hardware settings and numbers of points in that transition region. So that's really the best way to optimize a filter sweep and get the maximum instrument performance and speed out of that measurement. And certainly if you wanted to take it offline, you can email me separately. Hopefully my email address will be included in anything outgoing, and be happy to talk to you more about that.
Great. Thanks, Greg. We'll for sure share your email with everybody. And if anybody has questions that we don't get to, or you think of something later on, we'll make sure that we can get your question answered. We've got actually three more. So we have Victor who's asking if you have any advice on how to use a VNA and something else in order to perform de-embedded measurements of various components that are already part of a PCB assembly and may require unique planes of reference for each one.
Yeah, Victor, I think certainly that's getting well beyond the scope of our discussion here. It's kind of a deep dive topic, but yes, we do have that. I'd be happy to just talk to you about that offline. And again, probably an email correspondence would be a good first start. But yeah, we do have those capabilities, and we make it pretty easy.
Okay, yeah, thanks, Greg. I can provide Victor's email, and Greg, I'll provide you, Victor, I'll provide you with Greg's email, and then you guys can take the conversation offline. So we'll move on to the next question. During a bandwidth check of high gain amplifier, say 64 dB, um, how will the VNA be protected? By using an attenuator at the amp's output or some other method used? Per my understanding, VNAs will be injecting a fixed input into an amplifier.
Okay, yeah, that's a good question. It doesn't matter so much the gain of the amplifier, it's more, okay, how much output power does that amplifier provide? Our VNAs have a port threshold of pain of officially it's half a watt, but you can go up to about plus 30 dBm. Of course, even at those levels, I say threshold of pain, that's before you're actually damaging the device. But long before that, you're starting to get into regions of internal receiver compression, things like that. Generally, when you're doing higher power amplifier measurements, you'll use an external test set. So those directional couplers and things that I showed that are built into the instrument, you would just use external versions of those that have higher power capability. And typically on our higher end analyzers, we have direct access ports where you would use an external coupler and take the forward going wave, bring that into the reference input, let's say for port one, the measurement or the reflected wave into the measurement input for port one. So that would go directly to the VNA receivers. And same thing for the coupler at the output of your device under test. You do that. And at the output of the coupler, then you would generally just put either an attenuator, high value attenuator, or a load, some kind of a high power match, so that the instrument in no way sees any of that high power. It's all dumped into the load. So again, one of these situations where if you'd like to talk more about it, let's start an email discussion.
Okay, thank you, Greg. We've got one more question here. In regards to potential VNA connection port degradation due to use, will the device flag potentially out of tolerance conditions of the VNA connection port using the calibration test device? And would annual calibration evaluation typically flag an intolerance of the connection points on the VNA?
Yeah, the annual calibration would definitely do that. I think that's part of the calibration process. They'll actually examine the ports of the device in terms of measurement tolerances, make sure that the internal pins at those connectors have their proper dimensioning, as well as just visual inspection to make sure they're okay. We do have some new capabilities that we're introducing on our VNAs that allow us to actually compare results after calibration with the actual characterization information of the standards. So for instance, on our cal kits, particularly our manual cal kits, it comes with S parameters for each one of those standards, the open, the short, and the match standard. So after we do the full calibration, then we reinstall, let's say, the open connector, and we compare what the instrument is saying that connector looks like with what the characterization data says that device actually looks like. And if there's any deviation there, then you know that something is wrong, and you can just at that point think about inspecting like that open connector if it's been dropped one time too many off a tabletop, or examining either your cables or your connector on the instrument. We also have a new feature too that allows you to make measurements basically with uncertainty limits according to national traceability standards. So you put your device to test on the instrument, and depending on its loss and its reflections, you'll get these uncertainty bars around the measurement trace that will tell you if you're within spec or outside of spec. It's a really interesting, although a pretty advanced topic, I would say. It would definitely be of interest to anyone who's doing metrology type measurements in a cal lab. But that's kind of the advanced end of the thing. This new calibration check feature would be more useful to the engineer in his day-to-day work.
Okay, thanks, Greg. So I think that's all of our questions for now. I'll just give the opportunity for maybe one or two last questions, and then we'll wrap everything up. To the few people that we had ask some more in-depth questions, I'll connect you with Greg after the presentation, and you guys can continue the discussion offline and get more in-depth on those topics. Okay, I'm not seeing any more questions coming in, so I'd just like to say thank you again to everyone for joining us for the presentation, and thank you for Greg for being here with us today. If anybody thinks of any questions afterwards, please just reach out to myself or email marketing@testforce.com, and I'd be happy to make sure that Greg gets your question and he can provide you with an answer. If you're looking for more great technical resources like webinars, white papers, and app notes, you can visit testforce.com/academy. And we have some more exciting webinars coming up soon from the Rohde and Schwarz Everything Test Series. The next one will be on signal generator basics on March 16th, so watch out for that one if that's a topic you'd be interested in. Thank you, everyone, and I hope you have a great day.